Hello. In this video, we will cover section 7.3, which is on the central limit theorem for proportions. In the last section, we introduced sampling distributions. A sampling distribution is a probability distribution that shows the possible outcomes and its corresponding probabilities when performing a survey. We looked at sampling distributions in the context of simulating a survey. One observation from those simulations is that as the sample size of the survey increased, the sampling distribution looked more bell-shaped, like a normal distribution. So over here on the right, we can see the results from the simulations. So here's the second simulation, and here's the third simulation. You can see the probability distribution. We've got the possible outcomes, and although we don't have the probabilities over here on the right, you can convert the frequency to probabilities by dividing these numbers by 10,000, which is mentioned in this little bit of information here. And so technically this 10%, 30%, 20%, 30%, you can go through and you can turn the frequency into percentages, and then this is a proper probability distribution. Anyway, the point is that as we went from 10, a sample size 10 in the simulation to a sample size of 100, the probability distribution became more normal-ish. Like if you looked at it, it looked kind of like a bell-shaped curve. Well, it turns out that actually does fit a normal distribution, that it actually is bell-shaped given certain conditions. All right, and that fact, all right, that the sampling distribution fits a normal distribution given certain conditions, that's called the central limit theorem. All right, so that's what we're going to look at for the rest of this video. So what does the central limit theorem say? All right, so it says given certain conditions, all right, what are they? That they're up here at the beginning. So the survey must be random and independent. So the sample has to be collected randomly, and the observations must be independent from each other. The sample can be with or without replacement. It has to be a large sample. The sample has to be large enough there are at least 10 successes and 10 failures. I will make that clear in a later slide. And then the population has to be big relative to the sample. So the population needs to be at least 10 times the sample, assuming you're doing a sample that is without replacement. If those conditions are met, then the central limit theorem tells us that the sampling distribution is approximately normal, right? And that the mean for that normal distribution is going to be the population parameter P, and the standard deviation for that normal distribution is going to be the same as the standard error given here. All right, so what we can do is we can go through and we can start off by looking at a survey and thinking about what the sampling distribution would look like, and then we can transition over, we can jump over to a normal distribution if we have certain conditions that are met. And that's good news because we already know a lot about normal distributions, so that allows us to go through and use the normal distribution tools to do stuff with surveys. Hopefully that makes sense. Okay, so a brief review of normal distribution. So what do we know about normal distributions? What tools do we have? So a normal distribution connects probability to the area under the curve. So that's the most important result. All right, so for example, it allows us to go through and find the probability that a randomly selected woman would have a height shorter than 61 inches by finding the area under a normal curve that is to the left of 61 inches. All right, assuming that we've got the mean and the standard deviation entered into our normal distribution that fits for a standard woman. Okay, and so it just allows us to go through and connect probability to area under the curve. That's the most important thing. And then we've got the example there. All right, so central limit theorem tells us that we can use normal distributions for survey results. All right, that's just cutting right to the chase. That's what it tells us we can do. All right, so this allows us to go through and find the probability of a survey result by finding the area under the normal curve. So for example, suppose we had the situation that's in the last simulation from the last section. We've got 1,000 population, 25% are cat people, and we conduct a survey, one survey. All right, the central limit theorem allows us to find the probability that the survey will have less than 23% cat people by finding the area under the normal curve that is to the left of 23%. Now, if you go back and compare the language on this, on what I just said, to the language on the example on the previous page, the language is basically exactly the same. It's the exact same thing. So what we're saying is that we can go through and we can find probabilities by using area under the curve, under the normal curve for surveys, right? So that's the exciting result. All right, so let's spend another minute or two on the central limit theorem conditions, and then we'll do some actual examples. All right, so how do we go through and check the conditions are met? How do we do that? All right, let's talk about these. All right, so random independent. How do you tell whether a sample was collected randomly? You really have to trust the researcher. In this case, when it comes to doing problems in this class, in the problem, it will say the sample was collected randomly, and then you can just rely upon that and trust that's true. If you were to go through and use this in real life, then you need to talk to the researcher, make sure that they are going through and collecting the sample randomly. The large sample, how do you check to determine whether the sample is large enough? So we want to have 10 successes and 10 failures. What does that mean? If we go through and take the size of the sample and take the proportion or the percentage chance that, of something in the sample and multiply those two things, then the result has to be greater than or equal to 10. All right, that's what it means to be 10 successes. So that probably sounds like gobbledygook. Let's look at an example. So what we just talked about is we're doing a sample of 100 people in the cat person problem. So we've got 100 people. That's the size of the sample. And we're saying that 25% of them are cat people. So if you take the sample size 100, multiply it by the 25% of cat people, you expect to get 25 cat people. So that's considered to be 25 successes, right? The percentage is the percentage chance of getting a cat person. And if you do, then that's considered a success. Okay, and so and then you do the exact same thing for this second part. So we need 10 failures. So again, if you've got 100 people that are in your sample, and we've got a 75% chance that it's not a cat person or that it is a dog person, 100 times 75%, we expect to get 75 dog people. So 75 failures in this context. And so anyway, that's how you check for a large sample, is you go through and you do sample size times the population proportion, sample size times 1 minus the population proportion, and they both have to be bigger than 10. If you don't know the population proportion, then you can use the sample statistic instead. Okay, and then as far as the big population, to go through and check the big population, you can create a little inequality just like these ones above. And then the capital N here is going to be the population size, and the lowercase n is the sample size, and the population size has to be 10 times the sample size. And that's what this inequality says. Okay, so now that we know how to check for the conditions, we can actually go through and try using the central limit theorem to do stuff. All right, so suppose the population is 1,000 people, 25% are cat people, a random sample of 100 people is collected. Let's actually go through and find what is the probability that the percentage in the sample is going to be less than 23%. Okay, so before we actually jump in with that, we can go through and we need to check the conditions. So random and independent, look through here. Do you find the word random in here? Oh, right there. Yep, it's a random sample. So that means that the first criteria is met. Large sample. So we've got 100 people times 25% cat people. So we expect to get 25 cat people. That is greater than 10. And then we've got 100 people. We multiply by 0.75, so we get 75 not cat people or 75 dog people. That is also greater than 10. And so we've got the 10 successes and 10 failures criteria is met. And then the population, so we know that the population is 1,000, and we've got, if we do 10 times 100, that's also 1,000. 1,000 is greater than or equal to 1,000, so that condition is met, barely. Okay, so now we can go through what is the central, now that the conditions are met, what does the central limit theorem tell us? It tells us that we can use a normal distribution in place of the sampling distribution. The mean is going to be the population parameter, it's going to be the population parameter P, and the standard deviation is going to be the standard error. So thus, the mean is going to be 0.25. Where did that come from? It came from the fact that the population parameter is 25%. So that is given by this right here, 25% of the population are cat people. And then if you go ahead and take all the information and enter it in here, We've got the population parameter, 1 minus the population parameter, and n. You do that, and you're going to get 0.0433. Okay, so what we've got is we can go through and represent the survey using a normal distribution. We can go through and represent the possible outcomes of the survey using a normal distribution where the mean is 0.25 and the standard deviation is 0.0433. If that doesn't sound like a really cool, powerful result, it's just because you don't understand it. Because that is amazing that we can go from this information, we can go through and say, we want to do a survey, to the idea of being able to represent the survey outcomes, the possible survey outcomes, a probability distribution of survey outcomes using a normal distribution, with a given mean and a given standard deviation. That is amazing. That's really cool. Central limit theorem is one of the most important, most powerful results in the course. What are we going to do next? So to go through and actually calculate the probability, we need the normal distribution calculator in StatCrunch. So go ahead and power that up. If you need to, you might want to go through and review the using StatCrunch to find probabilities for normal distributions video. But once you've got the normal calculator loaded, we want to enter the mean into it. That's on the previous couple slides. We said that's 0.25. Enter the standard deviation into it. Enter the appropriate inequality. So we want less than or equal to, because we want to find the probability that we get less than the amount that was given. So that if you go back, what does it say? Less than right there. Okay, so that's why we're doing less than. And then the amount that was given, we want less than 23%. So put 0.23 in next to the inequality. Press compute. If you do that, the part of the normal curve that represents the region that we're interested in is going to be shaded. And you should also see a probability number that should pop out, which matches the area under the curve. Okay, so that is going to be our probability. Let's actually take a look though at the picture. So what we've got is we've got our normal distribution. We've got the mean that's on there. That's 0.25. We've got the standard deviation. All right, we've gone ahead and we've got the area that we're interested in, which is finding a probability that corresponds to getting less than 23%. Okay, so that's less than, that's going to be to the left, and then 23% is right on there. And then the beautiful, amazing magic of the normal distribution is that the area of that region is the probability of getting that outcome. All right, that's what we learned a few sections ago. That's another amazing, powerful result from this course is the normal distribution result. And so what is that area? That area is 0.32207875. And so how do we translate that into English? How do we go through and interpret that? So what that tells us is that there is a 32.2% chance that we get a survey that has less than 23% cat people. So let's just jump back here. Let's just tie it all together. So ask us to go through, suppose we've got 1,000 people, 25% are cat people. A random sample of 100 is collected. What's the probability that what's the probability that the sample is going to have less than 23% cat people? Well, the answer is around 32%. So there's a 32% chance that your survey, or that our survey is going to have less than 23% cat people, given all this information. That's magic. That is magic that we can do that. That's really cool. Okay, anyway, so let's look at another example. So Samuel Morse, the inventor of Morse code, claimed that the letter used most frequently in the English language was E, and that the proportion of E's was about 12%. Morse code translates each letter of the alphabet into a combination of dots and dashes. It was important that the most frequently used letter be the easiest to represent. In Morse code, the letter E is simply dot. To test Morse's claim, we took a simple random sample from a modern day textbook, not textbook, a modern day book. The sample consisted of 876 letters and 118 E's. So the proportion of E's was 0.1347 or 13.47%. Check the probability of getting a sample with that proportion of E's or higher, assuming Morse was correct, and e's occur 12% of the time. Okay, so what we want to do is we want to use the central limit theorem to do this. We want to go ahead and take this, the survey information on the previous page. We want to be able to apply a normal distribution to it. We want to be able to do area under the curve and turn that into probability. So that's what we want to do. We want to take all that stuff, translate it into normal distribution, and then translate area of the curve into the probability that we were asked to find. Okay, so random and independent. So check. Is it random? All right, so we took a simple random sample. So random, that's the magic word. So it is random. That gives us check for the first condition. Do we have a large sample? So if you take the sample size, which is 876, multiply it by 12%, you get about 105. That is bigger than 10. Take 876, multiply by 1 minus that for a failure. You get 771. That is also bigger than 10. And so the sample is large enough. All right, that criteria has been met. And then is the population big enough? All right, so this you can't really use an inequality here because we don't know what the population is. However, if you go through and you actually read between if you actually go through and dig into the information, if you're actually did this, the book contains more than 8,706. I can't say that, 8,760 letters. So the population size is sufficient, and that third criteria is met. Okay, beautiful. The central limit theorem conditions are met. What does that mean we can do? It means we can use a normal distribution to find the probability. All right. So if we're going to do that, we need to know what is the mean of the normal distribution. All right, well, it's going to be the population proportion. That's 0.12. And what is the standard deviation? It's going to be the standard error, which if you go through and do some number crunching, you get 0.010979. Okay, we want to take all that stuff and enter it into the normal calculator along with the 0.1347 that we were given. And boom, that's what we get. So what do we get? So we've got the 0.12, the population proportion is in there. The standard deviation / standard error, that's in there. We were asked to find the probability that we get at least the number of e's in the book. And so at least the proportion 0.1347. And then we've got the 0.1347 in there. And what we ended up with is there's only a 9% chance that we would get that number of e's, assuming that that Morse was right. So assuming Morse was right, and there's only the e's are 12% of all the letters in books, in the English language, in use of the English language, then if we were to go through, if he's right, and we took a random sample, then there's only a 9% chance that we would get a result that high. What does that tell us? How can we interpret that? Well, it tells us that that's kind of unlikely. It's kind of unlikely that we would go through, open a book, find a section that has 876 characters, look at those, and there's 118 e's, that we would get that number of e's for that number of letters. It's unlikely we'd get that number of e's for that number of letters if 12% of the letters are e's. Very unlikely. And so what that tells us is that makes us skeptical of Morse's claim. Morse is probably not right. It's probably the proportion of e's is probably not 12%. It's probably higher than that because that would make the percentage that would make this number, this 9%, would be higher if we moved. If you go back to this this picture here, if we moved this 0.12 up to 0.13, that would make the area here would become bigger. If we did that, if the mean was 13% instead of 12%. And so anyway, so the fact that we got a small outcome, a small percentage chance, that doesn't mean that it couldn't have been random chance. It could have been random chance. 9% does happen 9 times out of 100. But as far as statistics and critical thinking and kind of what you're supposed to learn in this class, when you get a 9% outcome, then it suggests that something a little off happened there. That's a pretty small number. That's going to be an unusual event, and so it probably means that something was strange there. And the thing that was most likely strange was Morse's claim. Okay, let's jump to the homework because that's what at least my students who are watching these videos. So I hope maybe some people that are not my students watch this, but assuming that my students are watching it, the thing they probably care about most is being able to do the homework. So let's do a homework example. According to a report, 40% of millennials have bachelor's degrees. Suppose we take a random sample of 800 millennials and find the proportion who have a bachelor's degree. Find the probability that at most 37% of the sample have a bachelor's degree. Begin by verifying the conditions. All right, so let's verify the conditions. So first of all, dig through here. Do you see the word random? Yes, you do. Check. So the random condition is met. Large sample. So we've got sample is 800. The population proportion here is given as 40%. Multiply those, you get 320. That's clearly bigger than 10. And 480, that's also bigger than 10. So the sample is plenty large enough. 800 is actually a big sample. As far as the population, so we aren't given the size of the population, but we're just given a blanket statement about millennials. If you think about what you know about millennials, there's millions of millennials, and so there's clearly much more than 10 times the population is clearly more than 10 times the sample in this case. Okay, so once we've got the conditions out of the way, what does that tell us? It tells us we can use the central limit theorem, which says that we can use a normal distribution to go through and find probabilities with surveys. All right, so we break out our, and what normal distribution, what information do we need about the normal distribution? We need the mean. All right, now that is given. That is the assumed population proportion. And we need the standard deviation. Which we're told is the same as the standard error, which if you go through and plug in the stuff, you get 0.01732. All right, so now that we've got that, to go through and actually find the probability, so we're asked to find the probability that at most 37% of the sample have a bachelor's degree. To find that probability, we want to find the area under the curve that corresponds to that information. And what is that going to be? That's going to be less than or equal to. So at most translates to less than or equal to. And then you want to put 0.37 into the normal calculator. If you do that, so there you go. You got the mean, you got the standard deviation, you got the less than, you got the 0.37. So this region here is going to represent the situation that we are interested in, which is that we would get a survey result that has less than 37% millennials with bachelor's degrees. All right, and then to go through and turn this into a probability, we want to know what the area under the curve here is, and that's what the normal calculator is for, and it tells us that it's about 4.16%. All right, so 4.16%. That is the answer. That's a pretty small number. So what does that mean? It means that you're unlikely to go through and do a survey and get a probability that is at most 37%, assuming that millennials actually have 40% of them have bachelor's degrees. So maybe that calls into question whether actually 40% of millennials have a bachelor's degree because the percentage chance is so small. Or it just tells you that if you're hoping or expecting to get less than 37%, you're likely to be disappointed because that is a very unlikely event. Okay, anyway, all that interpretation stuff you don't have to do for the homework. The homework is just going to ask you for this number here at the end. Sorry to scare you there. All right, so another homework example. A recent study reported that 22% of the residents of a particular community lived in poverty. Suppose a random sample of 200 residents of this community is taken. We wish to determine the probability that 27% or more of the sample will be living in poverty. And so it starts off, before doing any calculations, determine whether this probability is going to be greater than 50% or less than 50%, and explain why. And then when you're done with that, then go through and calculate the probability that you end up getting a sample with 27% or more who live in poverty. And you're told to just go ahead and assume that the central limit theorem conditions are met. So you can just skip over that part this time. Okay, so the 50% thing. So how do you go through and figure out whether this is going to be 50%? So there's kind of two steps to this. First thing you want to do is you want to compare these two numbers. So this is the population proportion. This is going to be the mean of the normal distribution. You want to see if this is bigger or smaller, right? Because you want to know, is this bigger than the mean? Is it to the right of the mean? Like if we were to actually draw a picture, a normal distribution picture, is it to the right of this or is it to the left of this? So that's the first thing we need to know. Is our sample to the right or to the left of the mean? And in this case, it's to the right of the mean. All right, so that's step one. Step two, we want to look at the type of inequality. All right, so we're asked to find 27% or more. So what does that mean as far as, if you imagine a picture, a normal distribution, or more means to the right. All right, so it means you're shading to the right under the normal curve, under the normal distribution. So what we're doing is we're taking something that's to the right of the mean and we're shading to the right of it. Okay, so to the right of the mean and then shading to the right. Now, if you could draw a picture if you want, or if you just close your eyes and imagine in your head, if you start off with something that's to the right of the mean, and then you shade to the right, is that going to be bigger than 50% or smaller than 50%? All right, so to answer that, what you need to consider is that the total area on each side of the mean is 50%. The total area. So in your picture, again, if you sit down and draw a picture to try and answer this, all of the area to the right of the mean is 50%, all of it. Now, if you start off with something that's to the right of the mean and you shade to the right of that, that's going to be less than everything that's to the right of the mean, right? And so if everything to the right of the mean is 50% and you're doing something that's less than that, then that means that the area under the curve has to be less than 50%. So that may be difficult to go through and do in your head, or maybe not. You can try it. But at worst, try drawing yourself a picture, and then you'll be able to hopefully see based upon your picture, that you can figure out whether the probability is going to be greater or less than 50% just by going through and just doing a little sketch or imagining it in your head. Anyway, that's what they want you to do for part A. For part B, it wants you just to go through to calculate the probability. It says, going to assume the central limit theorem conditions are met. To go through and calculate the probability, we need to know the mean for the normal calculator. The mean for the normal calculator is going to be the population parameter. That's 22%. All right, so we're told 22% of the residents of the community, meet that criteria. They live in poverty. And then to go through, and the second thing we need for the normal calculator is we need the standard deviation. To find that, you use the standard error formula. Go ahead and plug everything in, and you get 0.02929. All right, and then once you've got the mean and the standard deviation, we can then go through and actually use the normal calculator itself to find this probability by entering the appropriate information into the calculator. So, and the appropriate information is going to be the stuff that we're interested in. So what are we interested in? We're interested in that 27% or more. So you want to put 27% in, and then or more is going to be greater than or equal to. All right, so those are the four pieces of information you need to enter: mean, standard deviation, and then the region that we're interested in, which is going to be to the right of 27% or 0.27. And draw a picture there. So we can see there's our normal distribution. We've got the mean, we've got the standard deviation, we've got to the right of 0.27, and that's going to be about 4.4%, which is what you're going to be asked to just enter into StatCrunch to go through and answer the question. Or sorry, not StatCrunch, but enter into the homework to answer the question. As far as interpretation, again, that's a very small number. 4.4% is a very small number. So that either makes it likely that it's unlikely that you do a survey and you'd get 27%. That is unlikely to happen for you to get that extreme result. That's the way that I would look at that. So 27% does seem kind of far from 22%. And so what you've got is your expectations are that you would do a survey and you'd get something that high. That's unlikely. The way that you could kind of maybe translate this into something that is maybe more common that you've thought about is again politics. Unfortunately, is where we do a lot of surveying. So if you went through and someone told you 40% of the population are Democrats, and that you went through and you did a survey of 1,000 people, and they told you, you know, what's the probability that your survey result is going to be less than 35% Democrats, it's probably pretty small, because 35% is actually pretty far from 40%, you know, for a sample that has 1,000 people in it. Okay, so anyway, I don't know if that's helpful or not, but that's the way that you can interpret these things. Small percentage means it's unlikely to happen. It's unlikely that you would just do a survey and actually get that result. Okay, that is the video on the central limit theorem. Thank you for watching, and I'll see you next time. Bye-bye.